Sorry. Okay, share my screen.
Go for it.
All right. Can you guys see it good?
Yep.
Yep.
Oh, let me start my timer too so I can, sorry, make sure that I'm not going over. Okay. So yeah, mine is on the New Zealand Kaikoura earthquake, well, pre-earthquake before. So yeah, this is my second mapping project, and I actually liked this one better than the other one because the data set was easier for me to look at. So tectonic setting, a little bit of the background in this area. So New Zealand is just like really pretty cool. You've got pretty much the Pacific plate and the Australian plate coming together. In the north, you've got the Australian plate going over the Pacific plate. In the south, you've got the Pacific plate going over the Australian plate, and then right in the middle, kind of like a, as you can see in this figure on the right, a little bit of a strike slip, probably more oblique than just pure strike slip. Especially after looking at my area, you can kind of see good topography. This is an image of, you know, one of the fault scarps from New Zealand, and just spectacular, huge. I didn't like go on to this guy's website, so it's James Graby on inverse.com. I didn't read anything about any of these, but just a quick Google search, and this is what came up, and it's like, whoa. And I've seen, you know, a few of these before, but this is kind of the thing that's produced in New Zealand. My data sets that I used, the first one that I'm going to talk about is the Google Earth. I use this pretty frequently. I didn't actually take any images and have them geo-referenced. I just went back and forth between QGIS and Google Earth. And in QGIS, I made this outline of my project area, and it made it pretty easy to find just about anywhere I wanted to see in my mapping area. So it worked out very well. My other data set, I got this DTM, which this DTM was taken from actually airplane, just flying over and taking a bunch of pictures. And then I don't know how they do it, but they turned it into a DTM. And it's actually pretty good DTM. There are a few areas that have data missing, as you can see those rectangles in the middle of it. Also, wherever there was trees, it was a little more, I don't know, not very clear and not very good. Sorry. But overall, this was definitely a very good DTM. So the first thing that popped out to me when I opened this up was there's like, boom, right there, there's a pretty good fault that you can see right there. And then in addition to that, below it, there's, you know, kind of a big change between what's above it. Lower, you have kind of smaller rolling hills, less rocky mountains like what you have above. And then subsequently, right in line with that kind of major fault, you have this big drainage that goes right between those two different, you know, topographies. And so that was kind of first observation. And so then I was like, all right, first thing I'm going to do, I'm going to look at everything to the northwest of that fault. And so I started there because it seemed a little bit easier to see the drainages, and, you know, just overall easier because it didn't have as much vegetation. And so the DTM was a little more clear. And then afterwards, I went down and started checking out the drainages on the other side of the fault. And on a recommendation from Ramon, I really paid attention to the lower rolling hills down there and did quite a bit more, you know, drainage mapping there. from that, I was able to get a good idea about where I think there might have been some faults. And so I took off all of the drainages just so you guys could see it a little easier, a little better. And then when I zoomed out, oh, sorry about that, guys. When I zoomed out, I actually took the what I thought looked like they could have been possible structures that you can see here. And so after I put these down, I started zooming into them and started to try and find maybe some potential faults and see if those photolinears were actual faults or not. And in most cases, it turned out that there was pretty good faults there. Right here, I didn't put, you know, potential fault because it was pretty obvious to me that there was a structure there. So yeah, zooming in, that's what happened. But these areas right here didn't necessarily have any visible faults when I looked closer at them. Doesn't mean that there wasn't necessarily a fault there. I think, you know, and possibly there are some faults there. And actually the one, that blue egg on the far left of the screen, there was actually some faults in that area, but just not as easily seen or pronounced as some of the other areas. So my kind of determination between the different faults, the primary faults I did as areas that looked like they had quite a bit more offset on them, or, you know, maybe movement along those structures. And then also if they kind of shared the same general trend as that primary fault that popped out right at the very beginning to me. My secondary structures were oblique to that principal fault, or they didn't really have too much offset, or it was really hard to see if there was offset. And that's not always necessarily the case. There was some that were oblique to the fault, which I do believe were primary faults also. So my confidence rating, oh, 1 is supposed to be strong. So my strong confidence rating, that's where I could see an obvious fault scarp. And when it lined up with other obvious fault scarps, I was like, oh yeah, I for sure feel like that is, you know, a number 1. That's a strong. 2, distinct. I put that one, maybe it was lining up with some other strong faults, but it didn't have as much offset or didn't seem as obvious to me. But still, you know, I didn't need a profile tool to be able to tell that there was a structure there. I put a 3 or a weak confidence rating when I was, you know, not 100% sure if it was a fault or if it didn't line up with too much other things, you know, that would indicate a fault. So I did a lot of 3. That's what most of my faults were, especially when dealing with the secondary faults. I think they were a little harder to see, and my confidence was a little less in those areas. For my concealed faults, those were just when I had, you know, obvious faults on either side, and there was maybe some quaternary process that was covering it up, and I you know, could just put the dotted line right between the other 2 faults. So the area that I'd like to focus on, I'm pretty much focusing on just, you know, one area, the beach. But this was kind of a big challenge for me because there was, in my thought, there was a couple of possibilities of why I had some of these topographies here. It could just be that everything is being uplifted and the ocean is, you know, eroding the landform as it uplifts, and that's creating this linear feature, which, you know, is probably a good possibility. But so I went into kind of this 3D, I put the DTM in 3D and started looking at it, and I was like, okay, there's definitely some triangular facets here. And so I went back to QGIS and I mapped those in, and I started to use the profile tool to see if there was anything along these that would say, okay, there's a fault here. And so it wasn't just necessarily like a hard contact of going, you know, from, you know, flat to an uplift. I was looking for maybe like some offset along these that looked, you know, obvious. But as you can see on the far right of this, there was one that I definitely, using the profile tool, could see that there was a little bit of offset along that guy. And yeah, so I gave it a confidence of 3. But other areas of the beach that proved to be a little bit of a challenge. So, I mean, you can see here, you've got that little S curve. That's definitely a road. And then I was like, oh, there's a fault that's kind of going below it. And, you know, people are dumb. They always build on top of a fault. So that's probably a fault. But no, you go to Google Earth and it's just another road that is, you know, going the same direction. This road covered, well, both of these roads covered a large portion of the beach area of my mapping project. So yeah, I didn't put anything there. Then we go a little bit farther north along the beach, and this area was an area that I was a little more confident about. You can see there's some landslides, the brown landslides at the top, and I thought, okay, so if there's landslides, there's probably, you know, destabilization of some of these slopes from uplift maybe, or from, you know, movement. And then also, if you look right here, there's some lineations in the actual, you know, beach that I was like, oh, okay, that is lining up very well with some of the other major faults. And so I was able to be a little more confident in this area in calling out some of my fault calls. And also looking at the landslides, I started to look at those and found a couple of spots that also were being offset post landslide. So that was pretty good. But yeah, I guess that's pretty much what I've got and done. Any questions?
Thank you, Sean. It was almost exactly 12 minutes, so we have 3 minutes for questions. Again, students, it's up to you to ask the first few questions.
I have one for you, Sean.
Yeah.
When you were mapping the landslides in the area, I had the same mapping area, and it was difficult for me to differentiate like just landslides from normal like geomorphic, you know, processes, just because the area is so mountainous and there's so much going on in there. What were your signifying like factors to like decide, okay, this is a landslide? And I think you used the term poached landslide. This is a poached landslide.
Yeah, so looking right here, sorry, I'm gonna move you out of the way. So this one, I was like, okay, that looks like a fault scarp kind of, so I put this actually as a secondary fault, and then it looks like this block is kind of slumping down. And then also looking at some of the other ones, it was like wherever the topography was kind of lumpy, I guess, is kind of where I was looking at, you know, saying it was a landslide. And then I'd also do profiles along those landslides to see kind of the same lumpy texture, and then also notice if there was like a strong break in the topography at the base of it, because whenever there was a strong break at the bottom, I was like, yeah, maybe that's not a landslide, but yeah.
Awesome, thank you.
John, I have a question about the data that you used.
Yeah, Jackie.
This was, you said it had some high vegetation areas. Did you have like a difference in like ground versus vegetated DTMs that you worked with?
So right here is a pretty good, like, good to show that, because you have this whole area that's like really pixelated and not very good. That was like the highly vegetated area, versus everywhere else that's like maybe more grasslands. So wherever there's, and it wasn't just highly vegetated, it's just wherever there was trees. So I think that really kind of messed with their data in trying to make it, you know, look good. Did that answer your question?
Yeah, I had a pretty highly vegetated area, so I was kind of working with multiple DEMs from open topography. So I was just curious if you found one was more useful than another if you used multiple data sets.
No, I just used the one.
Okay, cool.
Then I had a quick question. You said you toggled back between your Google Earth and your QGIS a lot. Did you do any mapping on Google Earth and then transfer the lines over, or did you think it was more helpful to kind of just like toggle back and forth on the map to QGIS?
No, so what I actually did, I just toggled back and forth, but I did put my QGIS lines into Google, okay? So I didn't map on Google, I always mapped in QGIS, but I did, you know, move them over and see where they were and if it made sense, and so it was very helpful.
Yeah.
I guess it probably could have been more helpful to actually take each one of those images and put it in, but I wanted to focus more time into the actual mapping, so rather than trying to get a bunch of images. So.
Great.
All right, thank you. We're a little bit past the 15 minutes, so we do need to move on.
Thank you.
Thank you, Sean. Who would like to go next? Jackie.
Okay. Yeah. Screen. Okay, can you see that?
Yes, now we can.
Cool. Okay, so I'm going to kind of give a whirlwind tour of both of my projects, a couple minutes each, and really kind of go over my thought process and the approaches with both of these, because I thought it was really interesting on how different they both were and where I had to make modifications in my approach for both of these areas. So my first project is El Mayor Cucapa, or EMC, which is located in, I'm just gonna pointer options, there we go, which is located in Mexicali, so the border of Mexico and California. And on the right, I just made a quick Google tour. Oops, oh boy. No laser pointer. Okay, I just did a quick Google tour of the area, zooming in on this northern polygon. There was 2 polygons that I ended up mapping. So EMC is located in the southernmost portion of the Salton Trough. It's a pretty complicated plate boundary where you're transitioning from lateral strike slip motion of the San Andreas Fault and a divergent motion of the East Pacific Rise. It's a desert climate, so pretty arid, low rainfall, 6 centimeters per year. The data that I was working with is Google Earth, LiDAR from Open Topography, which enabled me to make some DEMs, hillshades, slopes, contour maps. And then I also used a couple combination scales for mapping 1 to 10,000 meters and 1 to 5,000 meters. So I'm going to just zoom in onto this northern area here in this northern polygon and show this aerial image, an example of an aerial image. So I found really good success using these aerial images for EMC. You're able to really see some really nice geomorphic features, which really helped me map. So really nice triangular facets, wine glass canyons, different sizes of alluvial fans, so large versus small. You can really see some nice contacts between bedrock, even some older paleo fan surfaces. So I really utilized these aerial images quite a bit for EMC, which were really helpful. I also used the DEMs and hillshades, this is a combination DEM draped over a hillshade for mapping. So this was really useful, teasing out some of more of these linear features that I saw that couldn't really be seen in the aerial images. So this is was really helpful for EMC, just teasing out some of those aerial lineations. And then looking at my workflow and zooming out so we can see both of the areas, I started with a geomorphic map. So using those aerial images and just flipping through all of the maps of the DEMs and hillshades and slope maps, trying to get a really detailed geomorphic map because there was such nice geomorphic features at EMC that were so clearly visible. So really mapping out all those alluvial fans, the drainage networks, and then trying to see where I was kind of seeing some maybe neotectonic features such as deflected drainages, some potential offset fault scarps, vegetation lineaments, tonal contacts. So this is really just a kind of a rough draft of wherever I was seeing these lineations in the landscape. So these purple lines are really anywhere I saw lineations in any of the maps with some specific vegetation contacts, deflected drainages. And then from there, I was able to build my final fault map, which the black and gray lines show my primary faults, and then the red show these kind of really low confidence secondary faults that kind of run sub-perpendicular to the primary faults. So this really striking, I interpret it as a strike slip fault running kind of at the contact between valley floor and this ridge here, where I saw most of those deflected drainages and some potential markers of offset. So this is EMC, really fun mapping area where I was able to really spend some time on the geomorphic features, which really helped mapping my faults. So moving on to Kumamoto, this is located in Japan. So another quick Google tour. I didn't mention this before, but it's a 2-to-1 exaggeration just to pop out some of those features. Another pretty complicated area. So Kumamoto is located in the southernmost island of Japan in the Ring of Fire area with subduction, volcanic arc, back arc extensions, all that fun stuff. And looking at the Google tour here, you can see it's a really diverse terrain. A combination of mountains, plains, active and dormant volcanoes in the distance, agriculture, urban areas. And then you're also dealing with a much different climate from EMC, so temperate, humid, high precipitation. So just really totally different mapping areas, which was really fun to kind of delve into what kind of methods might be different between the two areas. So the data that I used for Kumamoto is pretty similar to EMC with Google Earth images, LiDAR from Open Topography. DEM, I kind of talked about that a little bit when Sean was presenting. I had ground, unclassified, and vegetated options when downloading the DEMs. And I ended up using all 3 of those, mostly the ground, but for the presentation I show the full data set just because the DEM for the ground is really splotchy and not really filled in. But I did end up using this ground much more. And then hillshades, contour maps. And then I also noticed that I happened to map at a slightly zoomed out scale compared to EMC. So I wasn't really able to zoom in and get those finer details that I had in EMC. So another difference from EMC to Kumamoto is the aerials. So most of the geomorphic features that I ended up mapping were in this general area here. And you can see from the aerial that it's kind of hard to see what's going on because it's so highly vegetated. There's just a bunch of, green patches. So I didn't really use the aerial images as much for Kumamoto. As much as EMC. I did use them a little bit, but not as much for the geomorphic features. What was really helpful for me was looking at the DEMs and hillshades. So if you remember me a couple weeks ago lamenting about my hillshades, I did kind of figure out how to refine them. So that was a big win for me. So this is the kind of a more final product of that DEM and hillshade where you can, it looks a lot better. I have another view of what that looked like before if you want to look at that. So another challenge with Kumamoto was looking at the anthropogenic features. So I started to see some really nice lineations which run kind of along this area here. There's one kind of down here, over here, and I was like, these are really nice lineations, but they ended up being roads and power lines. So I spent a good amount of time mapping out all of the roads and power lines that I saw as to not confuse myself. And then from there, worked on my geomorphic map. So the key for this area was looking at the drainages, which enabled me to see a lot of deflected drainages, some potential beheaded streams, also some fault scarps. There were some ridges and these flat plateaus, which were also interesting. But mostly in this area, the drainages were what mostly guided my eye. So here's an example of some of those beheaded streams and deflected drainages. And then from there, kind of getting my rough lineation map. So these green lines are kind of a rough draft of anywhere I saw lineament. So in the hillshade DM, as well as using some of my geomorphic markers that I saw in the geomorphic map. And then from there, building my final fault map where I was seeing the fault. So this northeast to southwest trend strike slip fault that I was seeing pretty predominantly in this area here. And then just taking off those geomorphic features. And so just zooming out just to get the whole picture, here's this pretty intense map showing my roads and geomorphic features. And then looking at just the geomorphology, you can kind of see this really pretty prominent northeast to southwest trending strike slip fault. I did see this kind of secondary fault up here in the north. I wasn't quite sure what to make of it, and I didn't really know what it was. So I kind of labeled that as a secondary fault, but I really didn't spend too much time in this general area just because it was so urbanized and there wasn't a whole lot of geomorphology to map in this area. I also kind of labeled this area as a graben because there was such a high contrast between this plain or valley floor and then this higher rugged topography. So I thought that there might be some kind of downdropped block with this valley here, producing some relief in this area. And then finally looking at my final fault map, I have this strong fault kind of running right through where I see all of those deflected drainages in the topography, and then most of them are pretty weak and concealed. I didn't really have a whole lot of confidence with this area because there wasn't some really strong geomorphic features, for example, that I saw in EMC. So I was kind of cautious to label things stronger than they were with only just a couple of strong indicators of faulting in this area. So some final thoughts, just wrapping up, but looking at the two areas, one size approach does not fit all. To be really cautious in how you're mapping and looking at the methods. Climates, desert versus vegetated, will produce different areas where you have to be careful on how you're mapping. The anthropogenic features are also something to keep in mind. And then regional geologic features were something that was interesting. You can see that there's this really prominent lineation here in the regional features, and it was kind of interesting to think about if this could be a helpful guide or a bias or a little bit of both when mapping this area. Whereas this kind of guided my eye to where the faults might be, it also potentially biased where I was mapping because my eye was immediately drawn to that area. And then also mapping at different scales was something that was interesting between both of these projects. So with that, thank you to the instructors, Chelsea, Ramon, Rich, for building a really incredible class, all of our guest speakers throughout the semester, and the entire class for an enriching semester. So thank you, everybody.
Thank you, Jackie. We have about 2 minutes for questions.
Yeah, I had a question.
Yeah.
Sorry for whoever I cut off. If you go back to your last map of the faulting that you put up, yeah, that one right there.
Yeah.
It's just interesting to me because I did the same earthquake or the same
Cool.
rupture, and I noticed that you put your faulting across those deflected streams, like right at the mouth, and I sort of followed the more linear topography. And I was just wondering if you thought about that, or why you chose to put it farther back than I did. If you
Yeah.
yeah.
So that's a good question. And so when I first started mapping this, I was really thinking that the fault was kind of running right along that topography, which you mentioned. And I do think that the fault is primarily there. But for me, I wasn't really able to find a strong indicators. So those kind of beheaded streams and kind of contrast between the valley and the higher topography, in my opinion, wasn't as strong as this kind of area, because there was such a stronger lineations in the hillshades and DEMs, and also I had some stronger indicators of geomorphic features. So that's kind of where I had a little bit of a higher confidence interval. But
Sure. Sorry, I was just
yeah.
instead of just like at the front, I meant right here too.
Oh,
But
I see.
I hear what you're saying.
Yeah. Okay. Yeah. Yeah. It was pretty difficult for me, this whole area. So.
Me too.
Hi, Jackie.
Hi.
I had a question about the data sets you were using, and you talked about how you downloaded like the vegetation and the ground cover.
Yeah.
Did you find anything in the vegetation that you didn't see in the ground cover? Like, was that a good data set to have?
So what you're looking at here is actually the full data set. So it's the vegetated and the ground. When I was looking at, so I spent some time just mapping at the DEM scale, and I found that the ground provided a little bit more precision than the vegetated DEM. But when I layered on the hillshade, they both looked pretty similar as far as those data sets go. But I found myself mapping more with just the ground than the full data set for this area.
Okay, yeah, that's kind of what I was expecting. I mean, just the ground, you're going to see more details, but
yeah, exactly.
You still got both of them.
Hey, Jackie, quick question. So you've got your graben there. Is that, so also you've got your concealed secondary fault. Did you actually see any evidence for that? I mean, you have that entire thing as concealed. Did you just decide that, oh, there might be a fault here because this looks like a graben, or what was this determining factor on that?
Yeah, so for that area, it was really tricky because it was so urbanized. So I didn't really have a whole ton to go off of. That's why it was just such a low confidence for that. But what drew my eye to that area was just that the contrast in the topography. So going from that valley floor to a little bit of a higher elevation. And then also zooming in, and you can't really see from this image, but there are some really tiny subtle lineations in that area. So that's kind of where my eye was drawn to that. But it was pretty difficult, and I didn't really have a super high confidence in that area. But I think that there is something there. I just wasn't quite sure how strong.
Gotcha. Yeah, I can definitely relate.
All right,
Cool.
we should move on. Thank you very much, Jackie.
Thank you.
All right, we have a taker for next.
Sure.
Great, thank you, Rachel.
That was an awesome presentation, by the way.
Okay, so I'm gonna be doing a little bit of an update on my Parkfield 2004, and then because both of my mapping areas were in California, I'm gonna try to draw some comparisons between the two. So I'm first gonna show you some update on my Parkfield. I'm done with the fault mapping and everything, but I had used Google Earth a little bit more this time since we talked about it last time to see some of the elevation and the geomorph mapping. And then I'm going to make some comparisons between the Parkfield and the Napa because they both run either along the San Andreas or they're subparallel to it. And as I started doing more mapping in the northern section, I saw that it was a bit more complex and not looking at the earthquake that I did the pre-rupture fault mapping for, but I started to just see a lot of faulting like traces in the northern area where it was quite complex. So I knew there was probably something more going on, especially since it was right on the San Andreas fault trace. And so once I looked into it, I saw that there were actually quite a number of larger magnitude earthquakes that had an average of about like 22 years. I think the lowest one was 12 and the highest was 33. And then so it gave me a bit more insight into the number that I was seeing of the fault artifacts and then some of the quality of that. Some of the scarps were much well preserved than others. And because this is like such a hot button area, there's been a lot of research into it in the recent years since the mid-80s. And then it is along the San Andreas fault. Like I said, it's right lateral slip all the way through. But in Parkfield is special in particular because it's south of a creeping segment where that it just moves along coseismically but doesn't produce any earthquakes. And then the locked segment, which is the majority of the area where you get like singular larger events, but not a lot of smaller ones. And so what I have right now, because this is why I asked Sean before, I started the first several hours of mapping on the hillshade that I got from OpenTopo. And then after I got the Google Earth, the pre-rupture data, I started mapping on Google Earth. And so I did most of my draining and initial fault mapping on the hillshade, and then I started mapping most of the urban lineation and roads on my Google Earth. And, oh yeah, thank you, aseismically. And so what I did a little like tester that I could move all of my files that I made in Google Earth onto my hillshade. I'm waiting until the very, very end to do that because every time I make a change on the Google Earth, I'll have to redo it. And so I'm just waiting until the last second, but you can kind of see like if you were to overlay them that I have the drainages mostly on the right side and urban lineation on the left. And then so once I started going into Google Earth, I started to see a lot more of the geomorphic features in the area. And I finally found a sag pond, which I was pretty excited about, or what I think is a sag pond along this fault trace. And it helped a lot along this mountain front to just kind of give further indication that that's what I was looking at. And then another thing was some beheaded drainages, some offset drainages, what I think is a triangular facet. And this is like a lot better in Google Earth than in the hillshade. So I just started to do a lot of geomorphic mapping on Google Earth to try to find more indication of my fault traces in the like complex northern area. And then in the southern area, I took out the fault trace just so you can see the scarp line a bit more clearly. But I thought what I saw was a scarp, so I took a profile along it. And I think this right here is the scarp, and I measured it about like 9 meter offset. And if it were well preserved, although it's probably unlikely, I think the largest earthquake that hit the area was in 1857, and it was like the Fort Tejon earthquake, and that had a 9 meter offset approximately. So it could be a remnant artifact from that. And then for my primary versus secondary faulting in this area, I saw 2 to 3 large continuous north and northwest striking primary faults that cut through the middle mountain, and then also on the east and west side where there was a mountain front. And then these were really distinguished by the triangular facets, scarping, and my offset drainages. And then my secondary mapping is mostly concentrated to the northern area. And there's a lot of smaller subparallel to the main strike, but then there are a couple that I showed last time where they just kind of cut subperpendicular to the main fault trace. And so pretty much all I have to do left is just transfer my line work to Google Earth into QGIS, finish the report, and then analyze maybe some of the, I kind of want to go back just like really quickly and look at the secondary faulting in the northern half just to make sure that it might not connect to a larger continuous fault, or if it is secondary, and to leave it as such. But I did want to touch on the difference between the Napa and the Parkfield earthquake ones that I had. So my Napa 2014 earthquake was my first mapping one. And when I did some more research into the San Andreas, because I haven't had a lot of experience with it before, they broke it up into like the northern, the central, and the southern. And the northern area is where the Napa one is concentrated, and then the Parkfield is in the central segment of the fault. And I found this really cool graphic from USGS on the left that shows the probability of rupture for the San Andreas. And then right up here is where Napa is, and it's supposed to be kind of a smaller fault off of the Calaveras. And you can see that it has like 11% probability of rupturing again, which makes sense, I think, because since it's not as close to the main fault trace like the Parkfield, I didn't see as much deformation or secondary faulting. I just saw a couple of primary faults, and it was a bit more simple to map. But then in the Parkfield on the right, like I mentioned before, it's in this transitional segment between the creeping segment and the locked segment. And so it has kind of a transitional history where it has more larger earthquakes than the locked segments, but the creeping segment just has constant seismic activity without many earthquakes. And this is just more evident by just I have the plain hill shades on that you can see even outside my mapping polygon. There's a lot of distinct deformation and faulting, and there's just a lot going on as opposed to the Napa where it's mostly flat, and then you can kind of see a couple of the traces. But that is it.
All right, thank you, Rachel. We have quite a bit of time for some questions.
I found that when trying to do the geomorphic mapping in my study areas, sometimes it became difficult because my study areas were so big and it seemed like it took up a lot of time. How did you decide to do your geomorphic mapping the way you did, and have you decided to like kind of change it in the future, or do you think the way that you're doing it now is pretty prudent for like most areas?
Right. Yeah. I think you mentioned in your previous mapping that you used the base layer. I don't know if it was your DM, but mine was my SRTM, and it just showed the really large drainage traces, and I did that in QGIS. And then when I started mapping my geomorph in Google Earth, there was a lot more drainages, and it is a really large area. The north is very complex, so I just kind of constrained my geomorph to where I thought there might be evidence of faulting. So areas where I didn't think there was any, I didn't think it was necessary to map every single drainage. But then I did think it was necessary to map all of the urban lineation, because that kind of tripped me up a lot when I tried to find some lineation or vegetation lineation when I was doing any fault mapping.
Yeah, that makes sense.
Any other students that have questions?
Yeah, I've got a question. So in regards to mapping in Google Earth, do you think that it was like, I don't know, I'm sure it helped quite a bit, but would it have been better having Google Earth images overlaying on top of your DTM, do you think?
Oh, my page?
Uh-huh.
I did import the image overlay onto my Google Earth, and I didn't think it was super helpful, mostly because the quality of the Google Earth imagery was a lot higher than what I got from the hillshade, because I think it was a 30-meter hillshade for mine, so it kind of obscured a lot of the artifacts that I was trying to find. So I mostly just kept it where I imported the mapping polygon and then just mapped from that. And then I would toggle on the hillshade to kind of see if it matched up, but I didn't end up using the overlay on top of it.
Interesting. So you, I mean, it's pretty useful then, mapping in Google Earth, huh?
Yeah, and once I realized I could actually just like export all of it and import it into QGIS, and it maintained all of, like the little folders and everything, that was really nice, because I thought I was gonna have to do some weird MacGyver thing to try and get my lines to show up.
Yeah, because I did draw like a couple of lines in Google Earth, but it was like, I didn't actually figure out how to export any of that. I didn't really spend too much time into it either, because I didn't think it was possible, so that's cool.
Just like in the like very near future, you just have to save it as a KML instead of a KMZ. And then when you go to QGIS, you import it as a vector layer. And since I had mine in folders, it like subset all of them. You just change the color and the name.
Yeah, so pretty easy then. Right.
Yeah. The only thing is, and I didn't mention it in my presentation, when I mapped in Google Earth, I didn't make a difference between my secondary and primary faulting with just my line work, but I would name them as such. So when I import all the line work over, I can just change all of my secondary to the color that I like, all the primary back to red and everything. Which is
Good
why
job.
I didn't put any black ones on there.
Yeah, that was a challenging area for me, Parkfield, but I didn't have the DTM. Good job.
So I feel for you.
I would like to say also, in reference to a question that you had asked in an earlier presentation, it is a little bit more complicated, but from all of your work that you did on Google Earth, you can also create a DEM off of that, off of the elevation profile from Google Earth. So you could create those contour layers. I can send you a video that makes it super easy, because I know you were interested.
I think we did that in Field 2 last summer, if you remember.
Oh yeah.
Mm-hmm.
A really good
But pretty much
presentation.
just, like, the terrain was, I think, good enough for me, and then to see the elevation change via like contour lines.
Yeah, because for me, like you mentioned, that 30-meter DM is really hard if you don't have huge elevation changes. And so it's almost like you have to create your own with a better resolution scale. And I saw even you worked on that, like you with the transporting of the data. I think that's super useful.
Mm-hmm.
I had a quick question, Rachel. Did you have similar quality rankings for the Parkfield and Napa, or because the geomorphology and earthquake history is a little bit different, did you ultimately kind of use different metrics for assigning different qualities to your faults?
There was less geomorphic indication for Napa, I thought, and there was a lot of like the water or urbanization. And something I wish I did for Napa that I did for Parkfield was map the urban lineation. And that was a good note that I received back from that. So once I did that, it was helpful to kind of distinguish the difference between them. And then that helped my quality ranking a bit more, because I was able to determine if this is a fault, if this is just a line, which I didn't do previously. And then I'm starting to use I use the new one that we received instead of, so I've adjusted them a little bit, like the dotted or the orange, the secondary. And so now that I have a better understanding of secondary faulting as well, I think I'm getting a bit more tuned that it could still run subparallel. It doesn't always have to be primary. If it's a long strike, it could be secondary, just smaller.
Okay.
And so I've just like maybe been a bit more accurate with it this time around.
All right, great. Thank you. Should move on. That was great, Rachel. So we have Alana and Jenna left for today.
I don't mind going.
Great, Alana.
Okay. Share my screen. So I did the Bora Peak earthquake rupture, pre-rupture data, and This is just a quadrangle of the region, north going that way, so I could make the map bigger. And this is the south central region of Idaho, and it's an interesting area because it's different from the broad ranges of the rest of the topography, and it's more narrow, elongated ranges in a northwesterly direction. And it's all arid plains and rugged mountains, so that's sort of the climate. And the geology of this area is sort of a combination of volcanic rocks and Paleozoic, like quartzites and dolomites and limestones. So here's the overview of the mapping area that I did. I did 2 of the southern boundaries that you provided, Chelsea. And I split the fan mapping just into 2 different sections where I could, which was older and younger. And the data set that we used was DEM generated from the USGS air photos, and the USGS air photos were taken from Earth Explorer, right? So I changed up my confidence ranking on this data set from the last one, mostly because it was a pretty different geomorph environment, but also because it was normal faulting instead of strike slip. And so it's pretty much the same. I just decreased it by 1 point, but the geomorphic features have not really changed in ranking. So top quality is still beheaded stream channels, linear scarps, and all of that. And the weakest are like vegetation lineations and slope breaks. So this is an overview of the southern portion that I did. And one of the first things I did was just to point out all of the drainages, and while I was looking for any sort of offset stream channels or fan morphology. And one of the most helpful things that I found was sort of the difference in incision for across the faults where I could find it. It definitely seems like the eastern side is being uplifted more, if you guys can see that. And there's definitely some steep fan topography down here that I think buries a lot of the faults. And also another thing that I found really helpful was mapping with the contours for the fans, because I think a lot of the fans have been uplifted, and I think that it's easier to see with the contour mapping on top. Okay. And so here is the southern portion of the southern boundary. And you can see that I've just outlined a lot of the triangular facets, which to me indicated that this is where the fault should be. I removed the fault mapping on here so you could I'd either corroborate with my story or disagree with it. But I thought that typically the faults in this area were at the range front, because that seemed to be where the fans were steepening the most and where all those triangular facets showed up, and also the higher incision that was then leveling out down where the fans are. And then here's the northern portion. This part was a little bit more complicated because there were quite a few benches that I was uncertain about up here, and slope breaks, but I feel pretty confident that those are fault related and not changes in lithology. And the one that I was least certain about was this fault right here in front of this sort of uplifted block. And I think that it's uplifted because it is more incised than the fan surrounding it. And so that's why I think the, whoops. Sorry, I'm clicking all kinds of things. Okay, and that's why I think that this is where the fault is cutting in front of, because it is uplifting that block right there, and that a lot of the connecting faults are buried by the fans. I also thought that this,
at least on my screen, it's just showing your, like, the PowerPoint in your first slide.
oh, hold on one second.
There we go. Oh, it's just there a second.
Did that work? Hold on. Is that better?
It's coming. There we go. Now it says north boundary.
Okay, great. Well, I'll go back one more. So it says southern boundary north now on the screen. Okay. And then there were a couple spots where I had a potential fault here that that looked like there's a fan uplifted, and the linear nature was sort of cross-cutting topography, and also the channeling seemed to have started on the other side. And I'm not sure if that really is a fault or if it's maybe just an older fan surface, but I thought it might be faulting related. And here's the northern section. I have outlined a couple of the ridges that I think are tectonic because they are facing a different orientation than the rest of the ridges in the area. And I also included a lot of the stream channels here so you could see the incision comparatively. This area I was, the thing that I struggled with the most was deciding which were primary and which were secondary. Because as you can see on this fault up here in the ridge, there wasn't really a scarp. I just believe there's tectonic influences. So deciding whether or not that was primary or secondary was sort of difficult. And a lot of the more minor features, like where these the black dash line is, was definitely a fault, but didn't, based on length, was probably a secondary feature. So in my mind, these somehow connect, but I'm not sure how. And this one probably goes on off to the north into that boundary up there. And there are a few more triangular facets up here. And then this is just showing it without the fans, so you can see a little bit better the older fan surface and the lineations that I looked at that seem to be faulting related, right? And the incision on either side of the fault, which definitely seemed to be incising at a faster rate on the eastern side than on the western side, which to me also indicates that the east side is being uplifted, right? And then one of the other things that I struggled with was the idea of this being benches or scarps. So this is the same image, just with and without the fault lines that I've drawn. And so there are, this main fault up here was one that I was most hesitant about, because as you can see, it's just a downhill facing scarp, or it might be a change in lithology, or it might just be sort of mass wasting. It was really hard to tell exactly what it was, but I do believe that it was a scarp based on its orientation and the stream channel incision. And so some final thoughts are just that in less arid areas, you can expect scarps on a slow slip fault to be buried more rapidly. And so it's a lot harder to determine where exactly they might be. And based on my challenges with primary and secondary faults, are the range front faults usually the primary ones? Or is it that maybe the fault is propagating westward and the former primary faults are the ones that are actually up in the hills, and the range front faults are secondary? And any questions? That's it.
Thank you, Alana. We have quite a few minutes left for questions.
Well, I don't really know if I have a question right this second, but I just wanted to make a quick comment, Alana, about one of your final thoughts that got me thinking, and I thought that was really interesting, on how you mentioned the range front. Sorry if there's some landscaping going on in the background. you mentioned that the range front faults might not always be the primary faults. And I thought that was really interesting because I kind of struggled with that with one of my first projects, EMC. And also if it's primary or secondary, or if it's potentially an older fault versus an active fault. So that was something that I also kind of struggled with, was kind of looking at these range front faults and kind of defining them, and not kind of just assuming that they're the primary through going fault. So I thought that was an interesting thought that you just brought up.
Yeah, thanks. Because I usually approach the range front faults with that attitude, just like the main assumption that that is where most of the slip is accommodated.
Alana, I was just wondering if you could clarify why you have the black dashed line, so that's secondary. And it seems to run parallel to the two other primary faults, and it seems to have like a pretty strong, like just from the top image, you can see that there is some sort of linear feature there. So I was just wondering if you could explain your quality ranking a little bit more.
Yeah, that one I was less sure about because I thought it might be erosion related. I thought that might be like channel or rilling, and I was pretty certain it was a fault, and maybe it was just like erosion along it. But the other two seem to be like much sharper contacts, and I guess that one just didn't seem. I wasn't that confident in calling it purely tectonic.
Okay, but so then in terms of like why you ranked it secondary rather than primary, is that just again same reasoning? Because the orientation follows really well.
No, just because I ranked it secondary because it was shorter than the main fault that I put up there. That's really the only reason. And this one I ranked primary down here that is about the same length. I ranked it primary because I thought the orientation would connect it up with this fault up in the hills, but I just couldn't find the connection. So in my mind, those two are the same fault, and I'm just not seeing the connection. And this secondary one was sort of on its own.
Okay,
I have something similar in the one that you have secondary, I have as a primary, and I actually have it connecting further to the north. It almost like it's like a connector fault that connects the two. I also have two primary faults, one to the south and one to the west and the east, like you.
Okay.
But yeah, we kind of saw the same stuff.
Cool.
All right, we have 1 or so minutes left if students or instructors want to ask any questions. Otherwise, we can move on to Jenna, and thank you very much, Alana.
Thank you.
Okay, we just okay. So I decided to present on my most recent mapping project, the 2020 Monte Cristo earthquake that occurred west of Tonopah in Nevada. So I just kind of included a map to outline where the mapping area kind of generally is, even though it's hard to pinpoint exactly. Why does it, there we go. So just some basic area information. The earthquake itself occurred on May 15th, 2020 at 4:03, just from a simple Google search. General information, didn't look for much. Magnitude 6.5, and there are a ton of aftershocks going on, which is why I included this picture. I work for the Nevada Seismology Lab, and every day my email is just full of these aftershock notifications. So I thought that'd be a cool thing to include instead of just another mapping picture. But as many of you probably know, a lot of Nevada is characterized by the basin and range topography, where most of the ranges are bounded by faults. And there's a lot of volcanic or igneous intrusions throughout the state. And this area in particular of Monte Cristo is no different. So the data I used, there wasn't much available like we had to work with, so we just used the Google Earth and QGIS because it was the same Google Earth imagery as the one you would get on your desktop. So this data dates back to July 16th of 2016. And while there are SRTM files available, I included a picture of it. It didn't really help much. Yeah, I would have gotten much out of that. Maybe if the area was bigger and there was more, maybe less alluvial fan and more bedrock surfaces, then it would be more helpful. But it wasn't. And so using Google Earth, I mainly, for the elevations and everything, I use the desktop where you can zoom around and shift control click and kind of look. And that was probably as helpful as anything, honestly. So this was my general mapping area, kind of like a before and after shot. There's just a lot going on here. So tackling this was, yeah, it was hard getting started, I guess is where I'm going with this. But so originally I started with the more morphology, geomorphic layers, but then per instruction of Ramon during one of the presentations or check-ins, I said, okay, I'll start mapping more of the alluvial fan surfaces. So the naming for these is just very general. I really just wanted to get the different units down and start plowing my way through it. And so I ended up with about 11 different entries, different units that I tried to specify. About halfway through, I got in contact with Ramon and asked for some help, and that really paved the way and helped me take off with the rest of this. But just to kind of summarize what some of these layers are. So starting from the bottom, I have like a man-made deposit, and so there's a small mining town just west of this location, and so I've seen a lot of deposits and roads that have kind of affected some of these areas and have cut through the alluvial fans. So I just thought I'd mark those and get them out of the way so I don't tend to focus as much on them when I probably won't find much in them. There's also this main road, main dirt road that cuts through a lot of the alluvial fans in the mapping area. So I thought that would be good to outline as well. And then we also have this one really dark lava deposit on the western side that was easy to mark out as well. There's probably not much going on in there, but there's some drainage surfaces as well. And so moving up the list, we have the QOO and QO. And so these are mainly two different bedrocks that I identified through the area. One of them, the QOO, the green, has darker minerals, where the QO is mainly it's lighter, and it has maybe a more redder sediments that made it stand out more. And so if I go back, this is a good comparison to look at maybe while I talk about this. We have like the darker bedrock and the green like up in the northwestern corner, sorry, and then but a good area of difference is down in the southeastern corner. There's an obvious area of the darker bedrock, and then below it it's like that lighter yellower, maybe more orangey red color. So that was really important to I really wanted to differentiate that because that was spread out a lot through the mapping area. And so then going back up with the geologic features, there we go, or the units, sorry. I included this kind of QBQ basalt volcanic deposit, which really was evident in the most northeastern corner. And so I tried to follow that through the whole mapping area. But I've noticed a lot that some of these looked very similar to the darker bedrock, and so I ran into a lot of issues there. And so the main way I kind of differentiated it is the volcanics. were more consistent in color, where the bedrock had some darker minerals with some lighter ones. So the bedrock was mainly black and contained different sort of textures than the volcanic layers did. So that was my main differentiator. So yeah, like I said, this area is just kind of a lot, and I spent most of my time mapping this to try to pick out some of the faults. And so the rest of these layers are just kind of different alluvial fans that were deposited. I just tried to outline them, follow them through the mapping area. The last two QAs are like more of these alluvial runoffs, and they kind of start to merge together in some areas, and so that's why like more towards the top you'll kind of see like the purple cutoff and the lighter tan yellow run through, and that's just I'm more technical. I'm still not a professional, so my mapping's just, kind of a mess, but it served the purpose well, at least in some areas. And so after I did all the geologic units, I went in and continued with my drainages in areas where I suspected a fault, where maybe the units came together in a weird way or where they were separated. Something that caught my eye, I went ahead and kind of added in these like maybe suspected fault traces where I'd go back and look later, and I went ahead and did the drainages, tried to find some facets if there were any, to try and further support these faults. And so I stuck with the suggested quality ranking. And I, looking at these faults, I wish I would have been able to identify more in the alluvial fans. But the ones I found were primarily around the bedrock. So I stuck with primary and secondary faults. I mainly identified them as primary, although there was one secondary in an area I'll touch on later. If it was primary and strong, it was usually because the geologic unit supported it. There's triangular facets or other morphologic units present to support it as well. And then obviously I used weak if maybe it was just the geologic units pointing towards it, or something with less certainty, less proof. So this is just this is a mapping area I really wanted to highlight. There's a lot of different areas I could talk about because there's just a lot going on, but this one I spent the most time mapping it, and I still, I don't like this area. It's difficult for me. There's a lot going on. There's different areas of bedrock. There's different kinds of bedrock, it seems. You have these kind of alluvial fan deposits coming off of this bedrock on the green side, but I said those were volcanics. They look very similar. It could just be the bedrock coming up through the ground as other additional sediments were deposited on it. There's a lot that could be going on, but I'm certain there's quite a few faults going on in this area, especially because of the presence of all the triangular facets within the bedrock. Although some of them weren't completely developed, I've noticed that in a lot of these areas, there might be like just one or two complete triangular facets, and then other ones that are just maybe just starting to form, aren't, as certain. And so, yeah, but this area was a good one to highlight, just because there's a lot going on. This darker sediment is also unique. The darker sediment runoff mapped in yellow, it's also unique to this kind of corner of the mapping area. There wasn't too much of it in the rest of it. So that just kind of imposed the challenge of adding in more units and trying to decipher them and what's going on. This is also another area I wanted to highlight with primary and secondary faulting, and there was some triangular facets to support the primary. The secondary isn't as obvious, and I'm not as sure about it, but I would say if we qualify the changes in runoff and bedding above where we see this, where we see like the triangular facets and where the primary fault is, if we were to characterize that as a fault, it would be likely that the one below it would be similar, as there's kind of another like line to start of like the runoffs down the slope. Sorry, I'm like losing my voice. Anyway, and so just another area, I touched on this in the check-in, but I went back and looked because I noticed that there was a color change in the upper left-hand corner of these volcanics. And so originally, me and Professor Aaron Smith talked, and we were like, well, we could determine that this is a good area to say that there's no faults going on. And I would still say that, but I just wanted to go back and look at the shading difference. And while I'm sure that it's there, I'm not sure that it's anything significant. And this leads me to bring up the point that this using Google Earth imagery to map these, I commonly ran into the issue where like the shading, like the different lighting compiled by Google Earth, it never maybe fully lined up in some areas. And so the shading difference made it look like there was maybe a feature or something present in the alluvial fans when there really wasn't. And so that was something I commonly ran into and had to look out for throughout this mapping. And so just to sum it up, mapping, that I wasn't sure what I was going to get out of this class originally, but I'm really glad I took it and I learned a lot. And I'm glad I finally understand all of the mapping I saw throughout undergrad that maybe I never really touched on as more of a geophysics student versus a geology student. So, yeah.
All right, great. Thank you, Jenna. We have 2 or 3 minutes for questions. Let's open it up to students first.
I had a quick question. On your area 1 slide, when you had the 2 primary faults, what prevented you from extending the fault further to the northwest? If it was maybe you could have, if you wanted to like do it as a less confident fault or a lower quality ranking, because it still kind of looks like they might be cut off by it. So just like wondering if that maybe below your mapping had a better expression of the fault than above it.
Yeah, so just for sake of time and this presentation, I did kind of cut some of the areas short and just tried to get in the suspected faults. So I'll probably go back. I do agree that that fault probably extends a little more, and I'll need to look into that before all of this is due Friday. But I definitely agree. I'm just trying to get the basis down, and then, yeah, the units were most of this, so.
No, it looks tricky. You did a great job at mapping all of the fans and everything.
Thanks.
So in your map, all the polygons are like really well done. They're like all the lines are touching each other, like really perfectly. Did you use any kind of tricks or anything to like connect these lines and then fill it in, or did you just hand click every one of these connections?
Yeah, so I hand clicked a lot of them. It was obviously the feature of the shapefile that we started with. It'll just like kind of zoom over the area and it'll attach the line to the most recent polygon. And so that's, yeah, no, I made sure I was pretty thorough in the areas to get all of them to connect. There's a few gaps through the map that I didn't touch on that I wasn't really sure of, but for the most part, I just hand did it and started from one corner and went to the other, and yeah.
Well, good on you. That's nice. Yeah.
Wow.
All right, thank you very much, Jenna. Brings us to 15 minutes. So let's say thank you to everyone who presented today.
Good job, guys. A nice celebration of active faults, my favorite activity.
Yeah, great job, everybody.
So we have one more class on Thursday, and I look forward to hearing from the rest of you then. And otherwise, we can end class today. And again, don't forget that your reports are due on Friday. This will be the end of the class, end of the semester. and that's a very hard deadline with everything required to be due at ASU. So then you can finish the semester and we can finish all the grading and so forth. So, but anyway, great job today, everyone, and see you all on Thursday.
Hey, Chelsea, I got
Thanks,
a
everybody.
quick question.
Yes.
So I'm not going to be, I mean, there's a small chance I'll have reception on Thursday, but I'm probably going to be in an airport. Is it a bad, I mean, do I need to really put forth a lot of effort to try and?
That's okay. I understand. Maybe watch the videos after class, and if you do have signal, try to call in, but if you can't, then I understand.
All right, cool. Well, if I'm not here, thanks guys. This was a great class. Really learned a lot. Appreciate your guys' efforts. So.
All right, thank you, Sean.
I had a quick question about the resolution. So is it enough when I get mine from Open Topography to say which satellite it was from and that they were 30-meter?
So the SRTM is what you're talking about? Yeah, for the Parkfield?
Mm-hmm.
Yeah, so you should say that it's SRTM and Parkfield and then the date, and then the date of acquisition of the SRTM data set.
Okay. And then when I am doing the resolution from Google Earth, I just kind of see like the imagery day and the satellite. Should I look up the satellite and that will give me the resolution data from it?
Yeah, so you can do that. And you should, what is that noise?
My like phone is connected to my computer. I'm gonna mute.
Also then say the resolution of at the very least, the resolution that we georeferenced the imagery to that you are using.
Okay. So I know CJ did that with you guys last time, but I wasn't, since he did it, I don't really know what resolution the georeferencing was done at. So is there a way to find that out from like
Yeah, it's
the
in
drive?
the data. I don't know if Peter is QGIS here, but if you click, you like double click on the data set and then look around and you'll find a page with the metadata.
Mm-hmm.
And that will have your resolution on it. And so for SRTM, it will be, or depends on, I know because I know Ramon did that georeferencing. It'll either be in meters or units of degrees.
Okay.
Be on the same page where it tells you the coordinate system.
Okay, sweet. Thank you.
Is there anything you want to talk about, Rich?
No, I was just looking at my notes. Yeah, I mean, everything's fine. I was just